Welcome to my third video in my series on energy, and this is gravitational potential energy. We talked about it in a couple of videos ago. In this video, I'm going to do a couple more examples, get it hopefully a little more familiar in your mind. And what we're talking about here is gravitational potential energy. This is going to depend on the height above the Earth, not motion. That would be kinetic energy. So the more height implies more potential energy. We write that as potential energy. So that would be like if we put a heavy toolbox on a high shelf. It has a lot of potential energy. If it falls, it's going to make a lot of noise and hurt something. A book on a shelf, or a table, or for instance, a car at the top of a hill. All those have potential energy relative to the ground, relative to whatever the 0 point is. Our equation of potential energy is the mass times the acceleration due to gravity times the height. So M is going to be our mass, units of kilograms in the SI system, and G is going to be our acceleration, gravity, and that's an average. It's going to be 9.81 meters per second squared. It varies slightly depending on where you're at on the Earth, but that's the one we accept for most problems, unless we get down to really detailed level. This will work for 99% of everything. And then the height, that's going to be above H0, and that's going to be your reference point. It doesn't necessarily have to be the surface of the ground. It could be the change of potential difference between two shelves on a bookshelf. So H0 might be the third shelf up, and the height might be the fifth shelf up. And that's going to be in units of meters. So there's our basic equation. It's pretty straightforward. Now this G, which is equal to 9.81 meters per second squared, it's an acceleration, so we know velocity is equal to acceleration times time. So now if we evaluate this velocity at 1 second, we're going to get 9.81 meters per second squared times 1 second, and we're going to get 9.81 meters per second. So that's going to be the velocity after 1 second for an object in free fall. So that's just an object in free fall. And now the velocity at 2 seconds is equal to 9.81. This times 2, and that's going to be 19.6 meters per second. So that's our velocity after 2 seconds, and on and on. After 3 seconds is 3 times 9.81 times 3. That's 29.4 meters per second. So it's an acceleration just like a regular problem. And then we must always choose our H0, which is going to be our reference point. Not necessarily, like I said, the surface of the Earth. It's just wherever in our problem we would want to choose that at. And I'm going to do a couple of examples in just a second, and we'll talk more about this, finding the reference point of our 0 point. Okay, let's look at the example 1. A 15 kilogram, that's about 33 pounds, that's a pretty heavy toolbox, is on a shelf, and the shelf is going to be 2.4 meters above the ground level. That's about 8 feet. So it's kind of up there at the top. It's going to be a big reach. You'll probably have to get a ladder. And that's going to be above the floor. So where the floor is going to be our reference point. So that's going to be our H0. And this could be in a 10-story building. So H0 might be 300 feet up or 10 meters up, whatever it might be. So let's find the potential energy. So our potential energy now is equal to mgh. And here's our diagram. So that's our H0, that's going to be the floor. Like I said, that could be any level floor of any type of building. Here is our shelf. And there's our toolbox. And so the height of the toolbox is 2.4 meters. And we know it's a 15 kilogram box. So our mass is 15 kilograms, 9.81 meters per second squared, acceleration due to gravity. And then our height is 2.4 meters. So I'm going to get out my TI calculator here. Clear that. So 15 times 9.81 times 2.4, enter. That's equal to 353, and the units on that are going to be joules. So there's our answer to the problem. We got 353 joules. Now let's look at a second example. Here we've got a 1,600 kilogram car. That would be like your standard sedan that people would drive, our small SUV. So that's a pretty realistic number. And it's going to be 12 meters high in height. And this would be like 39 feet. Say it's parked in a parking garage above the ground. So we've got our car. Here's our parking garage. I'm not sure what level we're on, second or third level probably. Here's our car. Not a very good car. And then this is going to be the ground level. And so our height of our car up here, that's going to be H. That's going to be 12 meters. And so our H0 here is going to be the ground level of this parking garage. So our potential energy now is mgh. Our mass is 1,600 kilograms. G is 9.81 meters per second squared. And our height is 12 meters. Getting our calculator out, let's see what we get. I'll clear that. 1,600 times 9.81 times 12, enter. So that's going to be equal to 1888352. That's in joules. Now if we convert that to a scientific notation, taking our decimal point over there, that's going to be equal to 1.88 times 10 to the 5th joules. So there is the potential energy of our car, a 1,600 kilogram car, like a standard SUV, sedan, up 12 meters in, say, a parking garage. So the higher we go in the parking garage, the more potential energy we gain. So, hope you got a little bit of this, learned a little more about potential energy in this lesson, and I want to thank you for watching, and don't forget to leave any comments or questions. Thank you.